This module will briefly overview two major thermally direct circulations in the tropics, the Hadley cell and the Walker circulation. The primary driver of circulations on Earth is incoming solar radiation. More solar radiation enters at low latitudes, and the tropical atmosphere and surface experience a net radiative heating. In other words, more moist static energy enters via solar radiation than exits via outgoing long-wave radiation. At higher latitudes, north of about 45 degrees latitude, the opposite is true. More energy leaves the atmosphere via long-wave radiation than enters via insolation. This results in a meridional energy imbalance that requires the transport of energy from the tropics toward the poles. This requirement is the fundamental driver of global-scale meridional circulations. The typical boreal summer SST distribution is shown here, similar to others you've already seen. The warmest SSTs on Earth are generally near the equator and in the western portions of the Atlantic and Pacific Oceans. Insolation warms the ocean more in the deep tropics than at higher latitudes, and polar upper ocean currents transport the warm water along continental coastlines in the West Pacific and in the West Atlantic. The highest SSTs are located in the waters around the maritime continent in the Indo-Pacific and in the waters surrounding southern North America during boreal summer. Therefore, the deep, buoyant marine convection is most likely to be supported in the tropics relative to other regions on Earth, and more so where the SSTs are highest. The convection acts as the upward branch of a meridionally overturning, thermally direct circulation called the Hadley cell. The Hadley circulation transports air rich with moist static energy from low levels in the tropics to upper levels through convection, then transports the MSE-rich air poleward at upper levels. The flow slowly descends as it moves poleward, and the large-scale subsidence regions at latitudes near roughly 20 to 30 degrees north and south are near where many precipitation minima on Earth are located. Note that Coriolis acting on the low-level flow induces the background low-level easterlies that are present across much, but not all, of the tropics. The characteristics of the Hadley circulation, including its poleward extent, are governed by radiative convective equilibrium and eddy flow in the mid-latitudes. The Hadley cell has widened over the past several decades, as both mean global temperature and the mean latitude of eddy-driven jets have increased to higher latitudes. As we just saw, a Hadley cell exists on both sides of the equator. Somewhere in the tropics, the two cells converge and drive their shared upward branch. This is where convection occurs most and is called the Intertropical Convergence Zone, or ITCZ. The ITCZ moves throughout the course of the year in some parts of the world. For example, in the Atlantic, and climatologically speaking, the ITCZ reaches its northernmost latitude in boreal summer and autumn before returning toward the equator during the wintertime. Over Africa, the convection shifts between hemispheres over the course of the year. Similar behavior is also seen over the maritime continent, although the ITCZ there is also heavily affected by heating over nearby land masses that drive monsoons seasonally. However, generally, convection in the ITCZ also occurs mostly in the summer hemisphere, while rainfall is persistent year-round over the maritime continent itself. A notable exception is the East Pacific. There, the latitude of the ITCZ remains approximately fixed around 10 degrees north over the course of the year because SSTs in the equatorial East Pacific are generally too low to support deep convection, and there is no southern hemisphere SST maximum in the East Pacific. However, the frequency of deep convection is much less in the East Pacific ITCZ during boreal winter, shown at the top, than during the summer, shown in this panel here. All put together, the migration of the ITCZ implies that the upward branch of the Hadley circulation also migrates seasonally, and that the cell is often asymmetric about the equator. The seasonal asymmetry of incoming solar radiation has implications for the strength of the circulation in each hemisphere. On the right shows results of simple numerical simulations of the Hadley circulation with latent heating centered on the equator at 0 degrees, denoted by the red line. The circulation, in this case, is symmetric about the equator, as noted by the stream function here in the meridional direction and normalized. On the left is the resulting flow if the latent heating is centered at 10 degrees north, now well north of the equator, which is still the red line, a common occurrence during boreal summer. In this case, the summer hemisphere's Hadley circulation is weakened, while the cross-equatorial branch is much stronger relatively. We can see this in the stream function shown at top left. Low-level easterlies are present on either side of the upward branch in the symmetric heating scenario. And this is broadly true for the asymmetric heating case as well, except very importantly, a narrow region of surface westerlies can occur between the upward branch and the equator when asymmetric heating occurs. The westerlies may be found, for example, over the Indian Ocean during boreal summer and fall and flow into the frequently convecting maritime continent region. In some locations, especially over the East Pacific, a shallow return flow in the Hadley cell is also observed, like this here. This happens in particular where horizontal SST gradients are large and can sometimes be seen in the East Atlantic as well. This shallow return flow is itself part of a thermally direct shallow circulation driven by a pressure gradient force between the equator and the ITZZ. When convection in the ITZZ is weak and less mass is transported upward, the return flow is observed to be stronger. A mid-level inflow is sometimes also seen above the 0 degree C level as well. In idealized numerical simulations of a narrow tropical channel containing an ITZZ centered near 12 degrees north, the shallow circulation within the larger Hadley cell has important implications for meridional MSE transport. The numbers shown here are proportional to the flux of mass, water, or moist static energy into or out of the ITZZ via the low-level inflow of the Hadley cell, the shallow return above it, the mid-level inflow, and the upper-level outflow of the Hadley cell. The flux of MSE into the ITZZ region was an order of magnitude less from the northern cell than from the south. In the southern cell, about 1/3 of the incoming MSE from the south is exported through the shallow return flow. However, the same order of magnitude is imported through the mid-level inflow, such that the shallow circulations only have a small impact on the net poleward transport of MSE at upper levels. As expected, the vertically integrated transport of MSE was poleward both north and south of the ITZZ, with total transport being about 2.5 times greater in the southern hemisphere, and eddy transport being about 2.5 times greater in the northern hemisphere. And for these figures, you can think of the ITZZ as being a broad region located between 5 north and 19 north, with its center at the SST maximum at 12 north. If we zoom back out to our map of SST, we notice that most of the deep tropics is covered by ocean. A few places, equatorial Africa, the maritime continent, and equatorial South America, however, experience more shortwave heating. The maritime continent is also located in the middle of the warmest SSTs anywhere on Earth, and its mountainous terrain helps to force convection as local thermally direct sea breeze circulations drive convergence near the bases of large topographical features. As a result, the maritime continent is climatologically a location of year-round precipitation and is where the upward branch of the zonally thermally direct Walker circulation is located in the Indo-Pacific. The analytically derived response of the tropical atmosphere to equatorial and off-equatorial latent heating and convection can be considered. Suppose some heat source with a first baroclinic structure exists that is symmetric about the equator. We'll assume that y equals 0 here is the equator in these figures. And suppose that x equals 0 is something like the maritime continent, where lots of latent heating occurs in the atmosphere. This heat source can be denoted as Q. Shown on the left are the equations used to analytically determine the response of the circulation to tropical heating. They are just the horizontal momentum and continuity equations. The upward motion will be confined mostly to where that heating occurs. And that can be seen by the black contours, which are co-located with the red region, which indicates where the heating is occurring, with areas of subsidence further away from the central heating. Additionally, a far-reaching symmetric circulation response to that heating will occur. We can think of the heat source as convection over the maritime continent, and in response, a combined Kelvin and Rossby wave-like response will occur and be anchored to the heating. Whereas the Kelvin wave is the convergent part along the equator and the Rossby wave is the rotational part to the west of the heating and off of the equator, but symmetric. These waves are discussed with more detail in a different lecture series. For now, we'll say that the phase speed of the Kelvin wave would be 3 times larger than that of the westward propagation of the Rossby wave, and so the eastward extent of the zonal circulation response seen in either the top 2 panels will extend well to the east of the heat source, while the western part of the circulation is more limited zonally. The Rossby waves that develop to the west of the heat source help induce low-level westerly flow over the equator that is usually seen over the Indian Ocean. The response is very different if the heat source is placed off the equator, however, say about right here, at y greater than 0. If placed north of the equator, a zonal circulation still develops, but the western component of the circulation response in particular is asymmetric. Still, a zonal thermally direct cell develops near the equator. Meridional circulations also develop as a result of the heating. On the left is the meridional response to the symmetric heating case. The zonal wind and the stream flow is as we would expect and saw on a previous slide. And the pressure perturbation is at its minimum over the equator. With asymmetric heating, the circulation response only includes one primary Hadley cell that includes cross-equatorial flow. And surface westerlies are again found between the rising motion and the equator, as seen previously. Thus, both the major meridional and zonal thermally direct circulations in the tropics can be largely explained by the location of heating in the tropics. This heating is controlled largely by the distribution of land masses and SSTs. The zonally direct circulation is called the Walker circulation. The Pacific Walker circulation, seen at the center of this figure, possesses the basic characteristics seen in the previous slides. The low-level flow is driven by pressure gradients that are induced by the zonal gradient in SST, and therefore boundary layer temperature. Other upward branches also exist, for example, over eastern Africa or the western Indian Ocean, and this one here, most notably over the western Atlantic. These zonal circulations result in a reduction of background easterlies, or even mean westerlies, in the parts of the circulation to the west of the deep convection, for example, particularly over the Indian Ocean, and to some extent over the eastern Pacific as well at the equator. In the next module, we'll discuss how variability in the strength of the Walker circulation has ramifications on weather globally.